So in this video I'm going to be demonstrating how we conduct a ZE test or external loop impedance test on a single phase consumer unit along with the prospective fault current test. These tests can be done at the same time as they're done normally at the origin of the installation, and therefore we can do the ZE followed by the prospective fault current. So it's a live test and we need to be aware of that. And then we need to ensure that obviously our meter and our leads and probes comply with GS38. And just to prove that we do have a live supply, I'm using an approved voltage indicator just to check that we've got a voltage there at the incoming supply to the main switch, which we have, and approximately 230, 240 volts. So first of all, the ZE check or test. In order to do an effective ZE, we need to disconnect the main earth conductor coming into the installation, so that we then disconnect any parallel paths that may be present due to extraneous conductive parts such as gas pipes, water pipes, etc. So, as I'm disconnecting the earth conductor, we must maintain the isolation to the rest of the system. By removing this conductor, we're effectively removing the earth from the rest of the installation. So we maintain our isolation while we do this test, and now I'm going to remove the earthing conductor from the main MET, which is this one here, and have a disconnected earth there. And with this particular meter, and it does vary from manufacturer to manufacturer, we need 3 leads to test this. So we connect the earth lead of the tester to the earthing conductor, give it a good pinch, and then our line and neutral probes then go across the incoming supply. So if I place the probes across the incoming supply, my meter will tell me if I've got the correct volts before I commence the test, and it's telling me I've got the voltages, and now I can hit the test button. So at the moment the meter is sending a test signal to the external supply, to the supply transformer, the DNO's transformer. Now this reading here is exceptionally high. If this was a PME supply, I would be expecting a reading of 0.35 ohms or less. The reason we have such a high reading here is this is not a true ZE, and effectively what we're doing here is an earth loop impedance at the distribution board or the consumer unit via the wiring of this building. Hence the reading we get such a high reading. But the principle is essentially, as I've shown there, disconnect the main earth conductor and then across line and neutral and record the ohmic reading as ZE at the distribution board or consumer unit. So that's our ZE measurement. And then the important thing, of course, is once we've completed the test, recorded the result, we need to reconnect the earth conductor. So I'll just do that. So we reconnect the earth conductor. The next test I'm now going to conduct, as we're at the main incomer, we can then carry out the prospective fault current test. This is to measure how much current would flow in the event of a fault, either between a short circuit, line to neutral, or a short circuit between line to earth. So the 2 currents we're going to measure is the prospective short circuit current and the prospective short circuit earth fault current, I should say. We reconnect the earth for this test because we're reintroducing all of the potential parallel paths. This will have the effect of reducing the overall impedance of the installation and then raising the potential fault currents. So very important we have the earth reconnected. We don't need the installation energised, we can maintain isolation. It's the fault currents at the incomer that we're interested in. So again, using my meter, again this will vary from manufacturer to manufacturer. This particular meter, we have to select the individual tests that we want to make. So the first test I'm going to do is the earth fault current or prospective earth fault current test. The connections are exactly the same as I made for the external loop impedance. So we connect the this time to the MET and then cross line and neutral at the main incomer. Again, checking that we've got correct volts before we perform the test. And we have, so away we go. So if we can see on the meter in a moment, it still gives me a resistance reading, but we're not interested in this figure. We're now interested in the current reading, and it's telling me that the current, the fault current, would be up to 221 amps if there was a short circuit between a line and an earth conductor at this point. We now can select the short circuit current test. Again, the probes are in exactly the same position, but this time we're measuring the short circuit current between line and neutral. Hit the test button, and we see here a slightly higher reading of 304 amps. So we would record the highest of the two readings we've just taken, in this case 304 amps or 0.3 kiloamps, as the prospective fault current for that installation. So the purpose for conducting a prospective fault current test is to ensure that the devices, the overcurrent protective devices here, are capable of breaking or making that prospective fault current. So the figure here must be equal to or less than the stated maximum breaking capacity of these devices, which generally are up to either 3,000, 6,000 or even 10,000 amps.